Hello everybody, this is Dr. Imran. Welcome to ECEP channel. I'm going to present to you another interesting lecture of the course Electrical Engineering Fundamentals. And in this lecture, I will present about the resistances in series and resistances in parallel. First, I will properly explain about how the different resistances can be connected in series, and then I will further clarify this idea using some practical examples. I will then explain how the different resistances can be connected in parallel, and then further clarify this idea using some practical examples. Kirchhoff voltage law and Kirchhoff current law are the prerequisite topics for this lecture, and for this I recommend to refer to lecture 4 and 5 of this course. Let's watch the video and get some valuable knowledge about this topic. The resistors connected in series. Consider the combination of n resistors connected in series as shown by this figure. The series combination of resistances are R1, R2 up to Rn. And the voltage drop across resistor R1 is V1, the voltage drop across the resistor R2 is V2, and the voltage drop across resistor Rn is Vn. The series combination of these resistors are connected in series to the applied voltage source Vs, making one closed loop like this. So how we know that resistors R1, R2 and Rn are connected in series? For this, we take first the two resistors R1 and R2 and consider these two resistors are connected to this common point or node N. So if resistor R1 and R connected are only connected to this common point 1, and if no any other circuit element is connected to this common point N, then resistor R1 and R2 are said to be connected in series. And if, for example, there is another resistor like this connected to this common point N, then in this case resistor R1 and R2 will not be connected in series, but these will be connected in parallel in this case. In the same way, resistor R1 and the applied voltage source Vs are connected in series to this common point N, and you see that no any other circuit element is connected to this common point N, so applied voltage Vs and resistor R1 are connected in series. Similarly, R1 and Rn are connected to this common point N, and no any other circuit element are connected to this common point N, hence R2 and Rn are connected in series. This is one understanding of the circuit element or resistor connected in series. Another understanding is that there will be different voltage drop across the resistor R1, R2 and Rn which are connected in series. V1, V2 and Vn are dependent on the values of these resistances R1, R2 and Rn, and there will be same current I flowing across all the circuit element, making one closed path like this if we take the clockwise direction. So once we know that the resistances are connected in series, we can convert that into this equivalent circuit. You can see that it consists of the applied voltage source Vs in series with the R equivalent. R equivalent is the equivalent resistance of R1, R2 up to Rn, and this current I is the same, this current. So how we can convert this circuit into this circuit? For this, we need to understand about this mathematical work. We know that these resistances are connected in series to the applied voltage source Vs, making one closed loop or path. So it's a perfect example to apply Kirchhoff voltage law on it. And for Kirchhoff voltage law, I recommend to refer to lecture 5 of this course. After applying Kirchhoff voltage law in a clockwise direction, we get this expression. Vs is equal to V1 plus V2 plus Vn. Vs is the voltage of this applied voltage source, while V1, V2 and Vn are the voltage drops across the resistor R1, R2 and Rn respectively. We need to solve this circuit for current I. Then we use Ohm's law in order to find V1, V2 and Vn, and that is IR1 plus IR2 plus IRn. IR1 is the voltage drop across resistor R1, IR2 is the voltage drop across the resistor R2, and IRn is the voltage drop across the resistor Rn. Keeping current I common, we get this expression. Vs is equal to I1 plus R2 plus Rn. R1, R2 plus Rn can be replaced by R equivalent. Vs is equal to R equivalent into I, and R equivalent can be shown by this expression R1 plus R2 plus Rn. Using this expression, this circuit can be drawn as shown here. Vs, which is the applied voltage source connected in series to R equivalent, and R equivalent is the equivalent resistance of the series combination of R1, R2 and Rn. We take an example in order to further understand about the resistors or circuit elements connected in series. Use resistance and source combinations to determine the current I in the figure and the power delivered by the 80 volt source. We first try to understand about this circuit. It consists of 80 volt source, 30 volt source and 20 volt source. You can see the polarities of this 80 voltage source plus and minus, the polarity of this 30 volt source minus and plus, and the polarity of this 20 volt source plus and minus. This circuit also consists of a series combination of 10 ohm resistor, the 7 ohm resistor, 5 ohm resistor and 8 ohm resistor. You can see that this circuit is a closed loop. That is, if we take this 80 volt source and if we go in a clockwise direction like this, then this current starts flowing from here and flows across this loop and comes back to this 80 volt source. It means that this current completes one closed path if we consider this 80 volt source. As this is a closed loop circuit, so we can now apply the Kirchhoff voltage law. So after applying Kirchhoff voltage law, we get this expression. You can see if we take a start from this 80 volt source, then 80 volt plus 30 volt minus 20. The plus and minus of this 80 and 30 volt sources with respect to their polarities, and minus sign with this 20 volt is with respect to this polarity, that is plus and minus. VR10 is the voltage drop across this 10 ohm resistor. VR7 is the voltage drop across this 7 ohm resistor. VR5 is the voltage drop across this 5 ohm resistor, and VR8 is the voltage drop across this 8 ohm resistor. Solving the above equation for current I, 90 volt is equal to I into R10 plus R7 plus R5 plus R8. We take common I because same current I flows across all the circuit elements. Putting the value of R10, R7, R5 and R8 in this expression, then we can get the expression for current I, and this is equal to 90 over 30 is equal to 3 ampere. The second part of this question was to find the power delivered by this 80 volt source. The power delivered by this 80 volt source can be shown by this expression. P80 is equal to VI. 3 into 80 is equal to 240 watts. So the power delivered by this 80 volt source is 240 watt. We can also replace the above circuit by this equivalent circuit. It consists of equivalent voltage source which can be obtained from the three voltage sources, 80 volt, 30 volt and 20 volt, and the resistance are equivalent, can be obtained from the addition of the series combination of 10 ohm, 7 ohm, 5 ohm and 8 ohm, and that is equal to 30 ohm. Resistors connected in parallel. A circuit containing n resistors are connected in parallel as shown by this figure. First, we try to understand about this figure. The resistances R1, R2 up to Rn are connected in parallel to this applied voltage source having current Is. All the resistances and the applied current source is connected to this common point N. Here at this common point N, the applied current Is divides into various branches, I1, and I2 and In. I1 is the current across the resistor R1, I2 is the current across the resistor R2, and In is the current across the resistor Rn. If the resistances are connected to one common point, then there will be same voltage V, this one, across all these resistances R1, R2 and Rn. So such circuit element or resistances where the current divides into various branches like I1, I2 and In, well, while there is a same voltage V across all of them, will be called as circuit element or resistor connected in parallel. We can convert the above circuit into this circuit as shown below. It consists of the applied current source Is connected to the equivalent resistance Req. So how can we convert this circuit into this circuit? We need to understand about this mathematical work. So we apply Kirchhoff current law, and according to KCL, Is is an entering current to this node, while I1, I2 and In are the outgoing current to this node. And this can be shown by this expression. Is is equal to I1 plus I2 plus I of N. You can see this voltage V is common in all the terms. This is why, because voltage V will be same across the resistor R1, R2 and Rn. The above expression now can be shown by this expression. Is is equal to V over R equivalent, and 1 over R equivalent can be shown by this expression, 1 over R1 plus 1 over R2 plus 1 over Rn. We can also convert this expression by this expression. R equivalent inverse is equal to R1 inverse plus R2 inverse plus Rn inverse. We know that conductance G is the property of the resistance to allow the current across it, and conductance G is equal to 1 over resistance, while the resistance now can be shown by 1 over G. Using this relation, G is equal to 1 over R, this expression can be shown as G equivalent is equal to G1 plus G2 plus Gn. Hence, the Is can be equal to V into G equivalent. And from this expression, we can find the node voltage V, which is equal to Is over G equivalent. We take an example in order to further clarify about the resistor or circuit element connected in parallel. Calculate the power and voltage of the dependent source in the figure. This one is the dependent current source. We first try to understand about this circuit, and then we try to solve it. This circuit consists of a 6 ampere current source and 4 ampere current source, while it also has a parallel combination of two resistances, 3 ohm and 9 ohm, connected in parallel to another 15 ohm resistor, and this 15 ohm resistor is connected in parallel to the parallel combination of other 6 ohm and 6 ohm resistances. I3 is the current across this 3 ohm resistor, while Vx is the node voltage, which is same across all the circuit element in this circuit. We try to understand about another thing, and we point out two nodes in this circuit. That is, it will be node N1 and this will be node N2 of this circuit. So let's try to solve this circuit. You can see here that I have redrawn this circuit as shown here. I solved the parallel combination of this 6 ohm and 6 ohm resistor by using this expression, 6 into 6 over 6 plus 6 is equal to 3 ohm, and that is 3 ohm. I then further redrawn this circuit as shown here in order to further clarify about the above circuit. I clearly labeled two nodes N1 here and N2 here. I further labeled the current direction which are entering to this node and leaving to this node. For instance, the current of this 6 ampere is the current entering to this node, while the current across 3 ohm resistor and the current across 9 ohm resistances are outgoing currents, and the current of this dependent source is entering to this node. The current across 15 ohm resistor is the outgoing current to this node N1, and the current of this 4 ampere current source is also outgoing current to this node N1. Well, you can see that I have identified the voltage V with polarity plus and minus, and it is clear that if we have a single node pair circuit, then there will be same voltage V across all the circuit element. We apply Kirchhoff current law using this N node N1 and find the node voltage V using Kirchhoff current law. The Kirchhoff current law expression is shown by this expression: 6 ampere minus I3 ohm minus I9 ohm plus 0.9 I3 ohm minus I15 ohm minus 4 ampere is equal to 0. We write plus sign with the current of this independent current source and with the current of this dependent source here, plus 6 ampere and plus 0.9 I3 ohm. While we write minus sign with this current, this current, this current, and with this current. This is why, because all these currents are outgoing currents to this node N1. Once we know the node voltage V, then we can replace all these currents by these expressions. That is, V over 3 is the current across this branch, V over 9 is the current across this branch, V over 17 is the current across this branch. In this expression, the only unknown quantity is V. Hence, we solve this expression for voltage V, and the node voltage V is equal to 10 volt. The question was calculate the power and voltage of the dependent source. In this figure as shown here, we found the voltage of this dependent source already, which is 10 volt, and then the next step is to find the power of this dependent source. And for this we need to find IR3. IR3 is V over 3. It is why because the current of this dependent source is 0.9 I3. So that's why we need to find IR3. And let's find IR3 first. Here, if we know about the node voltage V, which is 10 volt, then we can easily find IR3 ohm, which is the current across this 3 ohm resistance. So V over 3 is the current across this 3 ohm resistor. So 10 over 3 is equal to 3.3 ampere. We now need to find the power of this dependent current source, which is equal to 0.9, 3.3 into 10 volt. 3.3 is I3 current, while 10 is the node voltage V. Hence, the power of this dependent source is equal to 30 watt. This is the end of this video. Make sure to subscribe, like, and share this video. If you want to ask something about this course, you can put your comments in the comment box. I will try my best to answer your comments. Thanks for watching this video and have a nice day.